Hey, Bogdanovsky here. Welcome to another video where we make linear inequalities easy just for you. So let's go ahead and begin. So when solving linear inequalities, think of how would you solve an equation, linear equation. If you haven't learned that, then watch another video. In this video, instead of using an equal sign, we'll be using signs that show less or greater or. You can see the sign less or equal or greater or equal. Sometimes, specific cases, especially when we talk about the restrictions domain, then we use that not equal symbol. So the solution, instead of being a specific number, as for linear equations, linear inequality comes with the set of numbers. So when we find a solution, we'll find an interval. So methods of solving is by algebra and by graphing. So those are two strategies that you can implement when solving inequalities. And first example, right here. So right here on the screen, you see x plus 4 is less than 6. So the question basically reads, find all possible numbers or maybe set of numbers that would satisfy the statement. So when x is increased by 4 by adding 4 to it, always it must be less than 6. So when solving inequalities, it's similar to almost identical with one exception that I'm going to mention later on. When solving it, you have to rearrange and isolate that statement for x. So 4, positive 4 is being shifted to the right side by subtracting. So that's why in the line below you see x is less than 6 minus 4. When you complete the takeaway, you get 2. So there you go. X is less than 2 represents set of all real numbers that are less than 2. Not equal, but has to be less than 2. And thanks to Desmos' beautiful software, you can see this on the graph where you see the entire region when X is 2 with dotted line that is shaded, showing values to the left on the number line. So that is the geometrical representation or graphical representation of the solution. The next example, x minus 3 is greater than 2. So when we solve it for x, we have to show what are the set of values or set of numbers that would satisfy this inequality where x minus 3 remains always greater than 2. So simplify it by removing negative 3 from the right side. So the next step shows 2 plus 3 on the right side, and x is greater than 2 plus 3. So 2 plus 3 is 5, easy, right? So you see it that solution here represents set of real numbers where x is greater than 5, not equal. It is 5 greater than 5. So 5.1, 5.0001, any number that is greater than 5. And again, thanks to Desmos graphic representation, you see dotted region and then shaded to the right of 5. So hopefully that makes sense. It's a simple example, I understand. Let's dive into a little bit more complex example where you see 2x plus 4 greater or equal. This time we show greater or equal, which means potentially you can see where this equation would hold. So what value the left side would be equal to the right side, and any other possibilities where the left side must be always greater, than the right side. So you're solving it by simplifying. So first thing is to separate variables from constants. So by removing 4 from the left side, you have 2x is greater or equal. You continue with that inequality symbol. And 6 minus 4 makes sense because you moved positive 4 to the opposite side. Then since we have to isolate for x, so we have to divide both sides of this inequality by positive 2. So when dividing by positive 2, we keep the inequality relations the way it is originally given in the question. So 2 over 2 is 1. So therefore x is greater or equal to 1, which means 1, x is equal to 1 is part of the solution, or any other number that is greater than 1. So graphical representation, now you see the shaded region with the solid line at 1 instead of dotted as in previous example, and it shows the region that is greater than 1, including number 1. Another example, negative 3x plus 5 is less or equal. So similar situation, less or equal implies that you could be equal at some point and less than that number. So let's go and start solving for it. So by separation, you keep the x variable with coefficient negative 3, but you keep it on one side, in this case on the left side, and then you would move positive 5 by adding negative 5 to both sides. So this is why you see in the line below negative 2 that is copied from the first line minus 5. And on the left side, 5 is gone. Since we have to solve it for 1x, then we have to divide both sides of that inequality by negative 3. So this is a very important step. That's why you see exclamation mark, because you divide by negative 3, so you flip the inequality symbol to opposite. So this is the only time that you have to remember the difference between solving equations as opposed to solving inequalities. When dividing or multiplying both sides by a negative number, you have to flip the inequality relation to the opposite. So now we have the statement that shows x is greater or equal to 7 out of 3. So it's a decimal number if you want to convert it, but mathematically speaking, exact solution is 7 over 3. Using Desmos as a beautiful software that allows us to see the solutions, you see the shaded region that is greater or equal. Therefore, you see a solid line, and then the number 2.333 represents the conversion to a decimal, 7 out of 3. But Desmos does not show the exact fraction, so we don't care about it really. What we need to care about it at this point to see what the graph really shows. All possible numbers that begin with 7 over 3 or greater than that. More examples where you have more complexity added to linear inequalities, where you have variables on both sides. So the first thing always is to simplify. So you must simplify, rearrange, and isolate it for x. That's the big picture. Okay. So how can you do that? You can expand this multiplication. You have to complete on the right side. And then you're going to remove constant number and then bring x's from the right side to the left side. So that's sort of the big plan. So we copy the left side, copy the inequality symbol, you complete the multiplication. And then you start shifting things around. So move variables to the left, move constant to the right. So in one step, we can show this next step forward. 2x minus 4x, as you can see, is less or equal negative 4 minus 3. And when you put it together, so 2x minus 4x is negative 2x. So this is why you see it here. And negative 4, negative 3 is negative 7. So inequality relation stays the same so far. But now, in order to solve it for one single positive x, we have to divide both sides by negative 2. So Bell rings, bing, 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 bing. We have to change the inequality symbol from less or equal to greater or equal because we divided both sides by negative number. That's the very important step to keep in mind. And showing on the graph, you see x is equal to 7 over 2, which is 3.5 in this case, and the region is shaded to the right because it's greater or equal, so you see the solid line on the graph. And let's move to this example where you see a fraction as a coefficient on the left side, and the left side must be greater or equal to the right side. So in order to find a set of numbers that would satisfy this inequality, we must simplify by using the rules of distribution. You would multiply on the left side 5 over 2 by each term, on the right side 3 times each term inside of the brackets. So that is the must step. You have to simplify, rearrange, and then isolate for x. So let's go and accomplish that. Now, instead of working with fractions, we have a beautiful option by multiplying both sides of this inequality times 2, right? So that step would eliminate fractions. So 2 times 5 over 2 would make that denominator to disappear. So if you multiply this entire left side by 2, and then if you multiply the entire right side by 2, you would always have that in mind that 3x and 3 comes from the first multiplication step and then times 2. So this is why you get 5 times x and 5 times negative 4. So you get 5x minus 20, less or equal. You copy the inequality sign the way it was given in the first place. So this is the same. And then 2 times 3x and 2 times 3. So therefore we have that 6x plus 6. Now we have to shuffle all the terms. So variables on the left side and numbers on the right side. So 5 minus 6x, that makes sense because 6x shifted over to the opposite side becomes negative 6x. Greater or equal than 6 plus 20 because that negative 20, boom, you have it. So 5 minus 6 is negative 1x, and 6 plus 20, 26. Now we have to divide it by negative 1, both sides, so that inequality relation gets switched to the opposite. Very important step. Hopefully this makes sense by now already. So x is less or equal to number negative 26. So on the number line, you would mark negative 26. You would include that endpoint and you would show region going to the left. So solving linear inequalities, or you will learn soon that any type of inequalities is about finding a set of numbers that would satisfy the statement, not just one particular value. And next example, which is the most challenging one because it involves double inequality. So what I mean by that, it shows that x plus 1 binomial is at the same time greater or equal than this binomial on the left, and also simultaneously it is less or equal than this. So you have to find what numbers would satisfy both requirements. So this is the little sort of secret formula in algebra that we now know how to use it. If you have that double inequality statement, you have to show how much is one inequality when x is greater or equal to a, because you read from the position of the x. To the left, I have to be greater than a, and to the right, I have to be less or equal to b. So that is why you have to solve two inequalities simultaneously at the same time. X is being greater or equal to a and less or equal to b. Boom. So that's why you define the first inequality, so you can call it sort of case one, and you do case two, and we'll do them both and find common solutions for intervals that we establish in the end. So the left side, 2 times x minus 3 less or equal x plus 1. So traditionally we have to simplify by expanding it. So we do that, and then we collect like terms on one side and the other group of like terms on the opposite side. So this is why you have 2x minus x, because of that x being shifted to the left, and negative 6 is transformed by adding 6 to both sides, so you have 7. So then you simplify. How much is on the left side? The like terms when you combine them. 2x minus x is 1x, and 1 plus 6 is 7. So this is the first case. X is less or equal to 7. That's not the end yet. And we have to solve the other inequality, the one that is boxed off by the yellow marker. So you go x plus 1 is less or equal, right? Then negative 3x plus 2 in brackets. So multiply first. So that's always, nothing changes as you see. Even the question is complex, much more complex. The first tiny example that we did on the first page, you do it through, go through the patterns, the same steps. So x plus 1 is on the left side, nothing to do here, times negative 3. Then reorganize, so negative 3x on the left, positive 1 on the right. So that's why you have x plus 3 and negative 6 minus 1. So 4x on the left and negative 7 on the right side. Now you divide both sides by positive 4, so we don't change this inequality relation, right? We keep it less or equal to the end. And now we have x is less or equal to negative 7 over 4. So on the number line, if you were to imagine, you have to show all numbers that are less or equal to 7, and at the same time, they are less or equal to negative 7, 4. Since negative 7 over 4 is less than 7, so any solutions for this would also be valid for solution for that, because I not only need to be less than 7, but at the same time have to be further down and be less than negative 7 over 4. So hence, this is the common answer to both, which makes sense. And when you use inequalities and Desmos, you see these beautiful two regions, and one is covered where the shaded area overlaps starting from negative 7 over 4 and including negative 7 over 4. So important, negative 7 over 4 is part of a solution, also any other number that is less. So hopefully this video makes sense to you now. You know how to solve linear inequalities. And before we go, don't forget to share this video with friends and like this video, subscribe to the channel, and immediately implement your knowledge by solving those two practice questions that you see right now. We'll see you again. Have a good one. Bye for now.